the two comparison tests. One is called the comparison test and one is called the limit comparison test. Okay, they make things a little bit easier, as you saw with that integral test problem we had. Can be used, right? So we're going to use this with series that are very similar. To geometric and p-series, but they are not exactly geometric or p-series. Okay? So if you see something that's very close, like this, is that a geometric series? No.
It's a p-series though.
No. Or is it a p-series? No. Because of the -1. But it's very close to 1, right?
Mm-hmm.
What p-series is it close to?
That's right.
Right? Okay, so we're going to compare the two functions. The two series, sorry.
Do we have the definition of geometric and p-series?
So the key here is which one of these, you got to compare them, bigger or smaller.
Bigger.
Now, does equal to matter in this sense?
You might have used on that one.
That's never been into here.
Okay, which denominator is smaller?
One.
Smaller denominator, right?
Yeah.
Oh, so that one's actually bigger.
Bigger number. Right? We did make a mistake over there. Oh well. So this is true, right?
Yeah.
Okay. If this converges, correct? It's a p-series.
Yeah.
We can say nothing about that one because it's smaller. Okay. There's no conclusion here. Okay. So we would probably end up using the integral test on that one, unfortunately. Or the limit comparison test, which I will show you. Okay, that might work here, because you end up with a limit of 1, and I believe that would actually show convergence. Yep. So the limit comparison test would be a good one here, but we're just focusing on the first. So, but if, let's say we have this series. And we compare it to 1 over n squared. Which one's smaller?
N squared plus 1.
Right, this one. So we have a smaller or bigger denominator makes a smaller number. Okay, so bigger denominator, smaller number. So if this is smaller, we have a convergence here. That means that this one converges. Okay, so there are times when you can use that to your advantage. You okay with that big idea?
So if it's less than and converges, or if
So yeah, so
less than and converges, then it converges, and greater than and diverges, it diverges.
right.
Okay.
So let's look at, very similar to the harmonic series, correct? Which one is larger?
And 1 over n minus 1.
Right. Since we know this diverges, and this one is bigger, that implies that this one diverges. That's the two relationships we look at. Bigger and diverges, smaller and converges. It's the easy way to remember it. So let me write out the theorem or the test, and then we'll do an example problem or two. So here's a comparison test. And remember, these are positive series. So that's all we're worried about here. So we're going to assume there's a capital M greater than 0 such that this relationship holds. And n is greater than or equal to n. But the key there is this relationship, right? If A sub n diverges, what happens to B sub n?
Diverges.
Yeah, because it's bigger, right?
Yeah.
Which one would have, oh, I'll let you write that down. So excited.
Why is it the range of n is greater than what weight does that have?
It's not random. It's if it wasn't necessary, it wouldn't be there.
Well, what? This is
I would assume, remember where we put that capital N in the geometric series?
Yes.
the creamer?
We put it right here, right? So we have to have this series extend beyond the initial term. It's just a formality. You don't need to worry about it. So if, which one of those converges? The other one does.
A sub n. If it is.
B
Or B sub n.
Yeah, B sub n converges, then A sub n also converges because it's smaller. Smaller?
We need to rewrite it though. It'd have to be B sub n is less than or equal to A sub n.
B sub n is bigger than A sub n. Since B sub n is above it, and B sub n is bounded or convergent, then A sub n also has to.
Oh, I see. Okay.
Yeah, we switched them. So that's the formal theorem. You get used to seeing those. meet the conditions of the test, which are pretty straightforward here. Greater than or less than. Pull the trigger. Okay. Let's look at a few. Okay, let's look at this series. So we see that we have both a p-series and a geometric series possibilities for comparison. Right.
Would we use the
And
geometric because it's 3 to an exponent?
we can try that.
That might
Right.
change from
Okay.
case to case.
So the geometric series,
Or, sorry, no, I meant use the other one, the P series.
okay.
Well, but if you use the geometric one, it might change from case to case.
P-series can too.
Can it?
Okay, so compare these two.
The one on
This-
the left is smaller.
Denominator is larger.
Oh, it's, yeah.
So it's going to be
Correct.
smaller.
Correct. It's larger.
What about this one? Same deal?
Yeah. Even the backwards. Denominator is larger, so it is smaller.
Smaller.
I have it right.
A quarter pound of meat is
Right.
less than a third
Yes, yes.
pound of meat.
Yeah, I was confused with you two.
Love the food analogy there, honey. Thank you. Yes, it's a larger denominator, smaller number. Okay, this geometric series, is it converge or diverge?
Well, it depends.
What's R? Your ratio.
Third.
Yeah, R is 1/3. So that geometric series converges.
Wait, how are you
When
able
your
to,
piece.
how are you able to say converted by the R?
The ratio is 1/3. If you rewrite this, 1/3 to the n.
Yes.
The geometric series test says that if that is less than 1,
Oh, yeah,
you converge. Okay. Is this smaller or bigger?
Smaller.
It's smaller, which implies
It converges.
converge. You have chosen wisely. This is the correct comparison.
Why don't you do the pieces? Why is it an incorrect comparison to the pieces?
Okay, this p-series does what?
You had divergence.
This is a half, right?
Yeah.
Diverges. This is smaller,
So you can't say, yeah.
Yeah.
no conclusion.
Okay.
You have chosen poorly. Indiana Jones there, right? You guys probably have no idea what I just
As
said.
it crumbles into bone.
Yeah, it's.
The gray.
Or
I mean, there were
last
bones
say
first.
Yeah.
There's nightmares first, and then there's bones, and then there's...
Okay, so yeah, choose wisely.
You ever see Raiders of the Lost Ark?
Do you follow it?
It's alright though.
Yeah.
No, it's not all right. I know you'll figure it out, but I think you're making it more complicated than it needs to be.
It's too abstract for me. I don't like it. I don't like
Good
abstract.
stats.
No, no.
Okay, plug a number in.
Okay.
Put 1 in. No, put 2 in.
Okay.
1 would be equal. Put 2 into that for n.
Well, I understand how you find less than or equal.
Oh, okay.
I understand that. It was like the geometric part that screwed my brain.
Okay. Do you understand the bigger, smaller relationship?
Yeah.
Then you have it.
I don't know, maybe you should.
Okay. Let's look at another one then. Let's look at this series.
Okay.
Gross.
I was wiping my nose and I wiped it on my watch.
Ew.
Well done. I thought you were
Hey,
talking
Monty.
about the man.
We
That's
did.
on the internet forever now.
Good.
Okay, what are you gonna compare that to?
Is that to the 1/3?
I want to
Yeah.
compare it to the 1 over n squared, but I don't think that's okay.
No.
Would it be 1 over n to the third?
So you have an n squared and a third here.
You have to do the outermost.
Oh, couldn't you just do 1 over n squared?
You just said that.
I think you have to evaluate it at the outermost, if you have to be 1 over n to the 1/3. Nice.
1 over n squared to the 1/3.
1 over n squared plus
Okay, we can try that. Let's see if we can figure out if there's a relationship.
Why'd you take the 2/3?
Because squared to the 1/3.
Oh, I thought that was a 1.
Can you show definitively that there's a relationship that holds there?
Considering we were going to drive the equation from that second
No.
equation from the original, there should be some sort of relationship. 'Cause we didn't just pull it out of thin air. There's still math involved, it's crazy. There's some sort of correlation, it's not a very strong.
It's gonna be 4, cube root of 4 over 1.
So wouldn't it just be,
What's the cube root of 4? Is that less than or greater than 1?
Plug 1 in, you get cube root of 4.
Yeah.
Plug 1 in, you get
1.
1.
So
The one on the
is
left is
bigger?
bigger.
Okay? Plug 2 in,
Or
cube root of
Cube root of
7.
7.
Or cube root of 16, which is 2. So then you get a half.
Whoa, you're really.
Whoa, Hunter.
Cube
Cube
root
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 of
of 7.
16.
And this is 2 squared 4, the cube root of 4. Which one's bigger?
Cube root.
Cube root, the 1 over cube root of 4.
Wait,
Oh,
bigger denominator.
Bigger number.
Yeah, I got it
Did
right.
you see it?
Oh.
Did it switch?
Yeah.
We can't say there's a relationship here. Okay, so we can't use this.
so what do we use? Wait, why can't we?
Okay? Is there something very similar to that that we know would definitely be less or bigger?
One over n.
Okay.
Plus 3.
Let's try that.
Because it switches back and forth.
Well, I thought they had to be like really closely related. You can't just do like.
Well, as long as you can show that there's a lesser or greater than relationship, you're good.
So the left is always going to be smaller.
Is it?
Yeah, cube root of 4.
The sign doesn't matter.
No, because if you plug in 1, you get the cube, 1 over the cube root
He's
of
right,
4.
for all real numbers greater
Yeah.
than 1 or.
For all positive numbers, the left is going to be smaller. Because it's going to have a bigger denominator.
For all real numbers?
For all positive numbers.
All positive integers above 1.
2, you get cube root of 7. Okay. And 1 over cube root of 7 over 1 over 2.
Cube root of 7 is less than 2.
Oh, no.
The
it's
cube root of
cubed.
is 2.
Oh no.
Oh, it's cubed.
So you get a smaller denominator,
Bigger number.
larger number. No, there's no relationship.
So much wrong.
Okay, so this is bigger.
What?
Yeah.
Okay, so if this we know diverges, right? This one is larger. What happens to it?
Diverge.
Diverges. I'm messed up, man. Okay.
Calculus.
You just have to play the numbers game. That's all it is. It's a numbers game.
I just plug in some values. See what you play around with.
Starting to draw, there's a whole lot of plug and chug these buttons.
Yeah, there is. With the tests.
How many numbers do you plug in to find out if there's a relation, like that positive and negative?
It's usually pretty obvious within a few numbers. Yeah. And that's just one way. Okay, let's look at this one and see. We're not going to get to the limit comparison test. But let's do it now.
No. Huh? No, I didn't usually pick up mine.
So this is a very good one to look at. What do you think?
You can do. Just as 2. Of course it's a 2.
I promise you.
It'd be easier to use the thingy instead of doing this.
Thinking instead of doing this.
The integral thing?
You could do the integral test here.
Yeah, it was one of the things.
Could you use the comparison test?
Yes.
What are you going to compare it to?
1/n.
Just saying that because of the last one.
Yeah, exactly.
Well, that's the only logical one we have because there's no other
Oh, okay.
series to compare it to.
Yeah.
It's P series or geometric. So which one's bigger?
You just
Okay.
have Lin out a lot.
Denominator is larger or smaller?
Larger.
Larger means the number is smaller.
So it's the less than.
Variation.
This diverges. Can I say anything about this?
Because it's larger. Yeah.
No conclusion. Because this is smaller.
So it's bigger converted, you can say it converges. It's smaller diverges, you can say it's diverges.
No.
If it's smaller and diverges, you can say the other diverges. If it's bigger and converges, you can say the other
B
converges.
so then is smaller.
Yes. Okay, so the comparison test has failed and we have no other options to compare that to. What are you going to do?
Integral.
Yeah, we're using integral test. What are you doing?
Is he on?
That's ugly.
2 to R, sir, is a limit of approaches.
Okay, so that would be your
Integral.
integral. So sometimes the comparison test doesn't work. That's why we have 9 different tests, right? Sometimes one of them doesn't work. So we're giving you like geometric and P series, and the nth term test should be very obvious when they need to be used. Right, P series, geometric, and then nth term. It's the integral test, the comparison tests, and then the alternating series test will be very obvious. So 4 of them are pretty obvious when you use them. The ratio and root tests are not. So you have 5 tests that you really have to think through. And we'll get to those others. But you're halfway there. We've done 5 now. Fortunately for you,
is ever allowed to say halfway there around our generation.
Hey, what?
No one is ever allowed to say halfway there, ever.
It's not our generation now.
Yeah.
It's
Not
Right.
all,
No,
that's
before.
That is a fast.
Rude.
millennials.
I think that's more of a regional thing.
Yeah. Really?
Yeah, where we live, we're more exposed to that song than if you go to Detroit or
Because
something.
they're hipsters, so they listen to Intel
Yes,
vinyl.
Detroit is a great comparison.
Like McLeod saying in a row is farm slang.
Huh?
Do you remember that? I said something in a row, and he goes, "Oh, you can't use that. That's farm slang." What?
Weird.
Used consecutively,
What?
but it never struck me that people
Did Mara?
outside of the Midwest
Yeah,
use in a
I'm gonna add
row
other.
because it's like for planting and stuff.
I figured
Oh,
that was
ducks
from
in a row.
ducks in a row, yeah. That's where mine might go.
That's not a farm slang. Maybe other.
So we usually do this section in 2 days. You guys are getting it in 4, which is fine, it doesn't matter. So I'm gonna add a couple of others, so you get practice with the other tests. So you don't just leave them in the dust.
That's a good song.
This is like the normal amount of homework.
You can't even like diss that. That's a
Not
good
really.
song.
Yeah, you're right. This is
Less.
still less than the normal.